Now that you're world experts at using the roadmap and limiting reactants and percent yield, it's time to finish off our discussion on initial stoichiometry by bringing up a topic that we could have brought up last term, but I always feel it makes more sense to bring it up after we have done reactions. And that's the concept of empirical formula. Now, empirical formula is defined as the ratio of atoms in a molecule as opposed to the molecular formula. Although that's not what the word empirical means. The word empirical actually means experimentally determined. And I want you to keep that as a backdrop as we go through. The main definition, ratio of atoms in a molecule, but the name comes from experimentally determined. Now we'll do a few examples, and I'm going to whiz through these because I don't think it's a tough concept to get. But if we think about the molecular formula, like for example C2H6, ethane. This is telling us in a molecule of ethane there are 2 carbon atoms and 6 hydrogen atoms. The empirical formula is, I don't care how many actual atoms there are in there, but there are 3 times as many hydrogen as carbon atoms. 6 hydrogen to 2 carbon is the same as 3 hydrogen to 1 carbon. The empirical formula is the ratio. The molecular formula is how many atoms are actually in that particular molecule. And the empirical formula is always related to the molecular formula by some factor that is a whole number. In this case, there are 2 empirical formulas in that molecular formula. Now, C6H12O6, that's the molecular formula, that's glucose. What's its empirical formula? Well, I hope you see that you've got 6 to 12 to 6, which is the same as 1 to 2 to 1. There are same number of oxygens as carbon, 6 and 6, 1 and 1, and there are twice as many hydrogens, 12 is 2 times 6. So what we're seeing here is that the empirical formula, the ratio is 1 to 2 to 1, and there are 6 empirical formulas in this molecular formula. Now, what's significant in this case about empirical formulas is that it does not define the molecular formula, and many different molecules can have the same empirical formula. So, for example, C2H4O2 has the empirical formula CH2O. The difference is that in C2H4O2 there are 2 empirical formulas, in C6H12O6 there are 6 empirical formulas. Another pair would be these ones, N2O4, empirical formula, NO2. And there are 2 empirical formulas in the molecular formula. But NO2 is also a molecule. That is the molecular formula of a different compound. Its empirical formula is NO2, and there just happen to be 1 of the empirical formulas in the molecular formula. Finally, and this might be a little confusing, but it's important to note that when you do organic, you start looking at homologous series that have nice little relationships between the numbers of each type of atom. And one homologous series would be that of the alkenes, CnH2n, twice as many hydrogens as carbons in every alkene. So therefore, the empirical formula of alkenes is CH2, and there are n of those empirical formulas in the molecular formula. Now, something that might seem evident to some of you, but is worth pointing out, that the relationship between the empirical formula and the molecular formula is the same as the relationship between the mass of the empirical formula and the molecular mass. So just to quickly throw these numbers there, molecular mass of C2H6 is 30. The empirical formula mass is 15. Right, CH3 is 15. And again, there are 2 15s in 30. In the same way, there are 2 CH3s in C2H6. Looking at C6H12O6 and C2H4O2, both of those have the empirical formula CH2O. C6H12O6, the molecular mass is 30. CH2O, the molecular mass, C6H12O6, the molecular mass is 180. CH2O, the empirical formula mass is 30. So there are 6 30s in 180, just the same way there are 6 empirical formulas in this molecular formula. And going to C2H4O2, molecular mass is 60. Empirical mass still 30, and now there are 2 30s in 60. In the same way, there are 2 CH2Os in a C2H4O2. And I can click on for completion 92 and 46. There are 2 46s in 92. 46 and 46 for NO2, that's 146 in a 46. And then for the CnH2n, there are N carbons, so that's 12. There are 2 N hydrogens, that's 2N, total of 14N. And of course, the empirical formula mass of CH2 is 14. And the factor to get from CH2 to CnH2n is N. Another concept that I could again have done last term is that of mass percent. Any percent is what you got over the total times 100. So we can look at a formula and we can say the mass percent of an atom X is simply the mass of X in that formula over the total mass of the formula times 100. For example, mass of nitrogen and dinitrogen tetroxide N2O4. Well, the nitrogen part is 2 N's, 2 times 14, which is 28. The whole thing is 2 nitrogens, 2 times 14, plus 4 oxygens, 4 times 16, gives us 92. Mass of nitrogen, 28. Total mass, 92, times 100, 30.4%. And of course, if I wanted to, the mass of oxygen, which is the only other thing in there, would be 100 minus 30.4, or 69.6. And it's worth a little bit of practice for you getting the mass percent of all those formulas. So I'll let you figure it all out, okay? What are the mass percents, or the percent by mass, of carbon and hydrogen in C2H6 and CH3, in carbon, hydrogen and oxygen in C6H12O6, CH2O, C2H4O2, and so on. So pause it and do those calculations. So hopefully you're back. For both C2H6 and CH3, it's 80% carbon, 20% hydrogen. For C6H12O6 and C2H4O2 and CH2O, it's 40% carbon, 7% hydrogen, 53% oxygen. And I want you to notice that the empirical formula is related to the percent by mass. If I know the percent by mass, I can actually figure out the empirical formula. I cannot figure out the molecular formula. Okay, the percent by mass is related to the empirical formula. We see the same thing for N2O4, NO2 and NO2. In both cases, 30% nitrogen, 70% oxygen, rounded to the nearest whole number. Okay, it doesn't matter that there are 2 NO2s in this molecular formula, 1 NO2 in that molecular formula. The percent by mass is the same. The percent by mass relates to the empirical formula. And then just for fun, the last one, 86% carbon, 14% hydrogen. Percent by mass, empirical formula, related with each other. Now, why is that important? Because we can actually get mass percent information experimentally. For example, 1.04 grams of chromium reacts with oxygen gas to produce 2 grams of chromium oxide. Well, the percent of chromium in that chromium oxide is 1.04 over 2 times 100, which is 52%. Mass percent of oxygen, therefore, would be 100 minus 52, or 48%. I can take that and get the empirical formula from it using that mass data, which I can convert into the mass percent data. I have 1.04 grams of chromium in that sample. I have 2 minus 1.04, or 0.96 grams of oxygen in that sample. As soon as I got grams, I can of course convert it to moles. So therefore there are 0.02 moles of chromium in the sample, because the molar mass of chromium is 52. And there are 16 grams of, molar mass of oxygen is 16, so that's 0.06 moles of oxygen in that 0.96 grams. So in this chromium oxide, in this 2 grams of chromium oxide, 0.2 moles of chromium, 0.06 moles of oxygen, there's your moles. There's the ratio, 1 to 3. That is that empirical formula. Knowing the mass, which we could get from the mass percent, we can get the moles. Once we have the moles, we have the ratio. There is a relationship between the empirical formula and the mass percent, between the empirical formula and mass data generally. Let's do another example in which we directly relate the percent composition to the empirical formula. New compound that contains CHO, 35.3% carbon, 5.9% hydrogen. Get the empirical formula. Well, we got carbon, hydrogen, and oxygen. It's 35.3% carbon, 5.9% hydrogen. All the rest is oxygen, which is 58.8%, which is of course 100 minus the 35.3 minus the 5.9. Now, once we got that mass percent, we can convert it into actual mass itself. And the easiest way to do that is to say, well, percent makes you think of 100, mass makes you think of grams. Let's consider 100 grams. In 100 grams, there will be 35.3 grams of carbon, 5.9 grams of hydrogen, and 58.8 grams of oxygen. Once we have grams, we can get moles. Carbon's mass is 12, so divide 35.3 by 12. Hydrogen is, of course, 1, and oxygen is 16. So in this compound, in this particular sample, there would be, in 100 grams of it, 2.94 moles of carbon, 5.9 moles of hydrogen, 3.68 moles of oxygen. We've got a ratio between the types of atoms. Ratio between the types of atoms is the empirical formula. Now, of course, this is an ugly formula if I was to use it, because you always want to have whole numbers. How do you turn a nasty ratio into a nice ratio? Well, first of all, you divide by the smallest. In this case, we'll divide everything by 2.94, and we get 1 and 2 and 1.24. Right? 2.94 divided by 2.94 is 1. 5.9 divided by 2.94 is 2. 3.68 divided by 2.94, 1.24. So it's nice there, nasty there. How do we do that? Well, you clear the fraction. Now, in this case, the fraction is obviously a quarter. Remember, in this experimental data, so 0.24 is pretty close to 0.25. So we'll multiply everything through by 4, and we find 4 carbons, 8 hydrogens, and effectively 5 oxygens. Thus, the empirical formula from this percent data, which is mass data, C4H8O5. So I said empirical means by experiment. Well, we can see that here. We use the observed data, the chromium and the oxygen, to get the empirical formula. We use the mass percent data to get the empirical formula. And here is another way in which the empirical formula is often obtained, so-called combustion analysis. Combustion analysis is where you burn something in oxygen. And what that means is that every single atom gets turned into its oxide. Carbon becomes carbon dioxide. Hydrogen becomes water. Nitrogen becomes NO2, chlorine becomes Cl2O, and so on. The only thing you can't figure out with combustion analysis is the oxygen, because of course you're reacting with oxygen, so the oxygen in the sample might just be tied up with the oxygen with which you're doing the reaction. But it's relatively simple to take care of that. So let's look at one. 3 grams of a new compound that contains CHNO subjected to combustion analysis. 6.6 grams CO2, 3.6 grams H2O were formed. Now what that means is that all the carbon in the new compound turned into carbon dioxide. So all the carbon dioxide came from this carbon in the sample. All the hydrogen in this 3 grams of the sample turned into H2O. So all the hydrogen in the H2O came from the hydrogen in that sample. So let's think about the carbon. All the carbon in the sample became CO2. 6.6 grams of CO2 is 0.15 moles of CO2. So therefore we had, because all the carbon in this came from the sample, there were 0.15 moles of carbon present in that sample. How about the hydrogen? All the hydrogen becomes H2O. Now it's a bit sneakier because there's 2 hydrogens in a water. So think about how to incorporate that too. Well, 3.6 grams of water, is 0.2 moles. Well, there's 2 hydrogens in every water. So if we have 0.2 moles of water, we must have 0.4 moles of hydrogen present. So we got the ratio between carbon and hydrogen. Well, how about the oxygen? We don't have a nice oxygen bit of data. So right, we can work backwards, because we know that in this 3 grams, there was 0.15 moles of carbon. 0.15 moles of carbon weighs 1.8 grams. So 1.8 of this 3 grams was carbon. We know that there were 4.4 moles of hydrogen present in this 3 grams. So the mass of hydrogen, tough one again, 0.4 times 1, 0.4 grams of hydrogen. So in this 3 grams, 1.8 grams was carbon, 0.4 grams was hydrogen, all the rest was oxygen. So the mass of oxygen, 3 minus 1.8 minus 0.4, which is 0.8 grams of oxygen. 0.8 grams of oxygen is 0.05 moles of oxygen. So now we have the mole ratio from our analysis. We got the carbons, moles of carbons, by looking at CO2. We got the moles of hydrogen by looking at water. We got the moles of oxygen by subtracting the mass of the carbon and the hydrogen, the 1.8 grams and the 0.4 grams from the original mass of the sample. Once we've got the ratio, divide by the smallest number, that's 0.05, gives us 3, 8 and 1. Empirical formula, C3H8O. Empirical formula is called the empirical formula because you can derive it experimentally. As our final consideration, it's nice to know the empirical formula, but what we're really interested in is not empirical formulas, it's molecular formulas. How can we use empirical formula to get the molecular formula? Well, I cast your mind back to the first slide where we talked about the factor. The empirical formula times a whole number gives us the molecular formula. The molecular formula is always a whole number of empirical formulas, so the molecular mass is always that same whole number of the empirical formula mass. Write it out again. Empirical formula times that factor is the molecular formula. The mass of the empirical formula times that same factor is the molar mass. Well, we can get the empirical formula. We've just talked about that. There are also ways to get the molar mass. When we talked about gases, we mentioned the Dumas method, or I might have said a slightly dirtier word for it, right? Where you know the mass of a gas, you know its pressure, volume, and temperature, you can get the molar mass, right? The formula that we got from the ideal gas law was molar mass is grams of the sample times R times T over PV. There are ways to get the molar mass. So you can determine the empirical formula experimentally. You can determine the molar mass experimentally. From that you get the factor. You take that same factor, multiply the empirical formula by that factor, and you get the molecular formula. Just to give you a fast example, compound with empirical formula CH2O. Discovered it in some way with that mass percent, with the weight data, with combustion analysis, whatever it might have been, was found to have a molar mass of 148. What's the molecular formula? Well, the mass of CH2O is 30. That's the empirical formula. Empirical mass is 30. Molar mass is 148. So therefore 30 times whatever our factor is 148. Factor is 148 divided by 30, 4.93. Well, this is experimental data. Obviously, that is 5. So therefore, this factor here is 5. So what's the molecular formula? It's the empirical formula, CH2O, times that factor that we got from the masses, 5, or C5H10O5. Hopefully that made sense. See you in class.